Hi, Mr. T here. In this video, I'm going to introduce the concept of rotational motion, and specifically we're going to look at angular displacement. So, well, let's get started. So, before we start, let's have a look at the circular wheel here on the right. So, let's assume that in the middle of the circular wheel is an axis. And the wheel rotates about this axis. So it doesn't move away from where it is, all that it does is turn. So the circular wheel has no translational motion. It has no velocity in a line, it has no acceleration, it has no force in a line in that direction. So what it does have though is it is turning. And that type of motion where it turns around a center point is called rotational motion. Now, rotational motion has its own set of quantities and equations. They're different, but they're similar to the ones that you learnt last year when you learnt about translational motion. So we had all of the kinematic equations we learnt last year. These rotational kinematic equations are very similar to the translational ones, but they have a whole new set of quantities. And the first quantity we're going to find out about today is called angular displacement. But before we do that, here are some other quantities that we are going to go over in the next few videos. The first one is called angular displacement, and it has the symbol theta. The second one is angular velocity, and it has this kind of Greek W symbol here. And then we have angular acceleration, alpha, inertia, this I, and torque is this tau, well, the Greek letter tau. They have their own units as well, and the base unit here is called rads, or radians. And then from there on we get radians per second, and that is similar to meters per second. And then we get radians per second, which is similar to the meters per second, etc., etc. Well, let's continue and have a look at what angular displacement is. Okay, angular displacement, what is it? So if we can have a look here at this disk again, and it's on an axle, it's turning around the axle. Well, actually it's turning around this way. This mass is attached to string around the outside, and as this falls down, it turns this disk. Now, when this falls down, the disk will turn through this angle. The angle that the disk turns through is what we call the angular displacement, how much the angle is being displaced. Now, angular displacement is measured in a unit called radians, and we'll look at that in the next slide. What's important to notice though is that if this disk is displacing an angle, that anything that was on the edge or the circumference in this will travel a distance around the circumference. We can calculate the distance that something would travel around the circumference here, and actually the distance that this has traveled around the circumference will equal the same distance that this has fallen down here, that this fell down here. That is the same distance as an object moved around the circumference in this example. But we can calculate that the actual linear distance, the distance in translational motion that this object on the circumference, that this point on the circumference has moved, is equal to the radius times the degrees. Oh, sorry, the angular displacement in radians. So, on the wheel above, at point T, has traversed 1.2 meters. So what happened is from here to here it's gone 1.2 meters. If the radius of the wheel is 0.2 meters, what is the angular displacement for this movement? Remember, angular displacement is going to be measured in rad. So when we get this answer, we're going to write it in rad. So we take this equation, the distance, which is 0.12 meters, that it traveled here, is equal to the radius, which is 0.2 meters, times theta, which we want to find out. So let's rearrange for theta. Theta equals d over r. Let's put our distance and our radius in. So our distance is 0.12 meters and our radius is 0.2 meters for every radian. I'll talk about why that's that unit soon. So we can calculate that the actual angular displacement here is 0.6 radians. But here's the point. What is a radian? So here is an example of our disk again. And a radian is actually the angle displaced when a point in the circumference has traveled one radius. So at this point has traveled a distance equal to the radius around the circumference, then this angle here will be 1 radian. And in fact, around a whole circle, there are 2 pi radians, or 6.28 radians. Let's have a look at this. There's 1 radian here, there's 2, there's 3, there's 4, there's 5, and there's 6 that snuck in there early. So there are 6 equivalents of the radius around the outside of the circle. Actually 6.28. There's a wee smidgy bit left here. So that number pi, okay, comes about from how many times the radius can fit around half the circumference of a circle. So we're always going to use 2 pi to multiply. So if this object has turned once, we can multiply it by 2 pi to work out how many radians it has gone through. So normally we would say there are 360 degrees in a circle. Now we say there are 2 pi radians, or 6.28 radians. And remember, our angular displacement is always going to be represented in radians when we give our working. So here's an example. What is the angular displacement of a wheel that rotates 3/4 of a turn? So remember, if this rotated 3/4 of a turn, how many of these 6.2 radians would it actually have displaced? Well, when we look at 6 and 3/4 of 6, we're going to be thinking about a number a bit smaller than 5. But let's calculate it. And we're going to calculate it using this. We're just going to go theta equals 2 pi of the revolution. A revolution is 1 turn. So here we've got theta equals 2 pi times 0.75. Theta equals 4.7 radians, or close to that 5 that I said. Well, let's put this in another way. A Ferris wheel rotates for 37 radians. How many turns does it complete? Remember again that there are 2 pi, or roughly 6.28 radians, for 1 turn. So we're going to rearrange this equation, and the revolutions, or the number of turns, equals the displacement, theta, divided by 2 pi. Let's put the numbers in here. We get 37 divided by 2 pi, and we get an answer of 5.9 turns. So if a Ferris wheel went around 37 radians, it would have done 5.9 turns. So we can easily change a turn or revolution back into radians by multiplying by 2 pi. So here's a couple of examples. Before we do the example, sometimes we're given a value in degrees. Okay, so we're given a value in like 270 degrees. If we want to change degrees into radians, we use this equation. We take the value in degrees, we divide it by 360, and we multiply it by 2 pi. An example here is, what is the angular displacement of a wheel that rotates 560 degrees? So because it's an angular displacement, I want it in radians. So I'm going to put my angle in degrees in the top. I'm going to chuck it in here, and I'm going to divide it by 360. That will tell me how many turns. When I divide the angle by 360, it tells me how many revolutions or how many turns. And then when I multiply it by 2 pi, it gives it to me in radians. And here we get 9.8 radians. Okay, so here's 3 examples here. So the wheel on the right has a radius of 40 centimeters. Remember, that is 0.4 meters. A mass attached to the wheel pulls the wheel by falling 1.3 meters. Now remember, if the string is attached here and this goes down 1.3 meters, then the outside of this must have moved 1.38 meters. So D equals 1.3 meters. R equals 0.4 meters. So D, R, I want to find theta. Theta equals D over R. Remember, the distance that this must have moved was 1.3 meters, and R is 0.4 meters. And we say that it's, because it's a radius, we say that here we have 0.4 meters for 1 radian. So 1 radian is, once we've gone around the circumference, 0.4 meters. So the answer here is 3.3 radians. Another example, the wheel on a car has a radius of 45 centimeters. The car rolls forward 2 meters. What is the angular displacement? Basically, it's the same again. We're using the same formula. So we chuck in now, except the car has rolled 2 meters. The radius is 0.45 meters per, so the meters per radian. So now we have a theta of 4.4 radians. And the last one here, a girl dives perpendicular into the water from a diving board at a pool. What is her angular displacement during this dive? So if a girl was diving perpendicular into the pool, she goes with her hands first, but she started standing up straight. She would have had to turn 180 degrees to have her hands going first instead of her feet, but dives perpendicular to the water from the diving board at a pool. What is the angular? You know what? I thought this said that she did a somersault. If she did a somersault, which I'm assuming here, then her revolutions will be 1.5 revolutions. So her angular displacement is 9.4 radians. If I was wrong and she didn't do a somersault, then it would have been 0.5 radians times 2 pi, which ends up giving us 3.14, or just giving us pi. So that's angular displacement. That's how we do some working to do with angular displacement, how we change revolutions to radians, how we change degrees to radians, and what a radian is. Remember, very simply, a radian is just an angle that has rotated that's equal to the radius around the circumference. And there are 6.28 radians in 1 complete revolution. So a radian is just equal to a specific value of an angle that something has rotated. Okay, so the next video we're going to look at angular velocity, okay, and theta. Yeah, we're going to look at, not theta, omega. So we're going to look at omega, and we're going to do some calculations with that, and I'll see you next video.